Hello there, Mr. Sutton here, bringing you the BC Calculus 8-2 Extra Practice Number 4 solutions on arc length. On this one, I need to set up and evaluate an integral to find the length of this curve over the interval from 0 to 3. So in order to use my arc length formula, I'm going to have to get the derivative of this thing. So using my power rule and a chain rule, that's going to be 3/2 times 1/3 out front. So that's 1/2. So we have 1/2 times x squared plus 2 to the 1/2 power. And now we have to multiply that by the derivative of x squared plus 2, so times a tail of 2x. At this point, let's set up our arc length formula. So we have the integral from 0 to 3 of, and now I have the square root of 1 plus dy over dx squared dx. And now for the calculator. To make things a little easier on myself, I've gone and entered this dy over dx as y1 and my y equals. Now I can just quit out of there, do math 9 for integral. We're going 0 to 3, 0 to 3, and let's see, we need the square root of 1 plus dy over dx squared, so alpha trace y1 to pull up that function that I just entered, square that, go to d dx, there we go, press enter, and that comes out to exactly 12. On this one, I'm trying to find the length of this curve, this integral defined function, and I need to set up an integral and evaluate it to do it. So let me start by getting the derivative of y with respect to x. Using my fundamental theorem, that's just going to be the square root of 3x to the fourth minus 1. And now I have to use my arc length formula, so I have the integral from -2 to -1 of the square root of 1 plus dy over dx squared dx. Now let me do the rest of that on the calculator. As a first step to doing that, I've actually entered my dy over dx as y1 in my y equals. And now let me do math 9 for integral. We're going from -2 to -1. And we've got the square root of 1 plus the derivative squared. So that's alpha trace y1, because that's where I stored my derivative. Don't forget to square it. Put an x on the d. Press enter, and that's going to be 4.041. For this problem, I'm trying to find the length of this parametrically defined curve. So I'm going to set up an integral and then evaluate it on the calculator. So let me start, since I'm doing arc length, I need x prime and y prime to figure this out. For x prime, this is going to be a little bit of a mess. Using our derivative rules here, we've got the derivative of ln of this stuff first. That's going to be 1 over secant of t plus tan of t times the derivative of secant of t plus tan of t. So that's going to be secant t tan t plus secant squared of t. And don't forget, we still have that random minus sine of t kicking around out there. That derivative is going to be minus cosine of t. So this is kind of a mess. You could leave it like this since we are using the calculator, but if you want to simplify, you can do so by first factoring a secant out of the numerator to get tan of t plus secant of t inside. And then that's really the same thing as secant of t plus tan of t, so that parentheses in the denominator can actually cancel out, leaving us with a much nicer looking function of secant of t minus cosine of t. All right, so that'll be a little bit easier to enter in the calculator, which we will do in a moment. Now let's find dy over dt, which is just going to be a much easier one. This is just negative sine of t, the derivative of cosine. At this point, we set up our arc length integral. So that's going to be the integral from 0 to pi over 3 of, and now we're going to have the square root of dx over dt squared plus dy over dt squared, dt for the differential, and now let's go and do the rest of this on the calculator. To make my job a little bit easier, I'm going to enter my x prime, which was secant of t minus cosine of t, in y1. So secant, there is really no button on the calculator for it, so what you can do is do cosine of x, close that parentheses, and then put a -1, or you could do 1 divided by cosine of x, same thing. And then we're subtracting cosine of x from that. And for y2, this is my dy over dt that I just figured out. So that was negative sine of t, basically. Quitting out of there, we're going to now do our integral. So we're going to do math 9. We're going from 0 to, let's see here, pi over 3. So we have a pi divided by a 3, and we need a square root. And now dx over dt squared. Well, I stored dx over dt as y1, so let me do alpha trace, pull up y1, and then just square that, so I don't have to mess around with squaring trig functions. Plus, now we need dy over dt squared, so alpha trace, I stored that in y2, square that, and then go over here and put a d with an x, press enter, we get 0.693. On this one, we're trying to find the length of this curve, which is a function of an x function defined in terms of y, and we want that on the interval from 1 to 2. So to do this, for my arc length formula, I'm going to require the derivative of this thing, dx over dy. So let me go through and get that. Using my power rule, this first term, I'm really having 3 times 1 over 6, so 3 over 6, or 1/2 y cubed. For this next one, I can think of this term as really being 1/2 times y to the negative 1. So the derivative of that would be negative 1/2 y to the negative 2. All right, so there's my dx over dy. Setting up my integral now. I've got the integral from 1 to 2 of the square root of 1 plus dx over dy squared. And we have a dy for the differential. Now it's time for the calculator to work its magic. To make things go a little more smoothly, I've entered my dx over dy function as my y1 in my y equals. And notice that I've entered this in terms of x rather than y. That's okay as long as I use x's for everything in my integral. My calculator will do the same thing with it that this integral is doing down here with y. All right, so quitting back out then, we're going to do math 9 for integral. We are going from 1 to 2. We've got a square root. We have a 1 plus, and now we have dx over dy squared, so that's going to be alpha trace y1 squared, because that's where I stored my derivative. And we have an x to go here, because I defined my functions in terms of x. And press enter. Comes out to 1.417. To find the length of this curve, I'm going to set up and solve an integral with my arc length formula. Let me first start by getting my derivative, dy over dx. I'm going to need that for arc length. So going from left to right, we have derivative of sine of x, which is going to be cosine of x. And then for this next piece here, I'm going to have to use the product rule. So let me set up my box and ribbon for that. So in general, I've got u prime v plus uv prime. So for my u and my v, I've got a negative x and a cosine of x. And for u prime and v prime, we've got negative 1 and negative sine of x. Multiplying those out with the ribbon now, we have minus cosine of x plus x sine of x. And I just happen to notice that we have a cosine minus cosine, so that's going to cancel. So let me just simplify this to x times the sine of x. And now I'm going to set up my arc length formula. So that's going to be the integral from 0 to pi in this case of the square root of 1 plus dy over dx squared, dx. And now let me do the rest on the calculator. So far I've done math 9. I've entered 0 and pi as my limits of integration. We have a square root of 1 plus, and now I need dy over dx, the derivative. So I'm going to open a parentheses, and we have x times the sine of x. Close the parentheses on the sine. Close the other parentheses around the x times the sine. Don't forget to square all that. And then let me put a dx over here, getting a grand total of 4.698. To find the length of this function over the interval from 0 to pi, I need to first get the derivative in terms of y, so dx over dy. That's going to be cosine of y, cozy, I guess. So now let me set up my arc length. So that's going to be the integral from 0 to pi of, we're going to have 1 plus dx over dy squared inside a square root, and we have a dy for a differential. So let me do this on the calculator. So here's what this looks like on my calculator. I did math 9 to get integral. I have 0 to pi, square root 1 plus, and now I have a cosine of x, and notice I have to close a couple parentheses here to square that. I actually could have done that without so many parentheses. We could have done no parentheses there, no parentheses there, and that would have accomplished the same thing. Either way, we have a dx over here, and that gives us a grand total of 3.820. For this one, we have a curve parametrized by x equals something and y equals something else, traversed once for the interval from 0 to 2 pi. Basically, we want the total length of this curve. So for that, I'm going to use my arc length formula for parametric functions. So that's going to be the integral from a to b of the square root of dx over dt squared plus dy over dt squared dt. So let's see here. Our integral length, or our interval, is going to be 0 to 2 pi. So I have the integral from 0 to 2 pi. And I'm going to have a square root of a whole bunch of stuff with a dt outside. So I need to take the derivative of x. That's the first thing in there. So we've got our x right here. This derivative now going from left to right. We're going to have 6 times cosine of t. And then, let's see, using the chain rule here, this is going to be minus 21 cosine of 7t. And all of that's being in a squared parentheses, squared brackets. Next, we're going to add the derivative of y squared. So derivative of y, that's going to be, let's see, negative 6 sine of t. And then using another chain rule, this is going to be positive 21 sine of 7t. All of that in a squared brackets. And the good news is we don't have to plug this in the calculator. We just have to match it with one of the answer choices. So let's see here. I have a 6 cosine of t minus 21 cosine of 7t. That is only going to match answer choices C and D. And then between the two of those, I need a plus. We need a negative 6 sine of t and a 21 sine of 7t being squared. And that looks like it's only going to be answer choice D, which is different than C because we have some squaring going on, so you can't just distribute this negative. So choice D then. On this calculator-based free response problem, R is the region in the first quadrant bounded by this 4x minus x cubed plus 1 function from above and the line 3/4 x from below. Based off of all this, our first task is just to find the area R. So for this, we're just going to use an integral. The basic idea is we're going to do integral from left to right of top function minus bottom function. So we need to find our limits of integration. One of them is going to be 0. We're bounded by the y-axis on the left side. But we need to find the x value where these two functions intersect as well. So to make my life a little bit easier, I'm actually going to rename these functions. I'm going to call this top function up here f of x. And I'm going to refer to this line here as g of x, so I don't have to keep writing the whole thing out. And now I want to figure out where f of x intersects g of x. So I need to see where those equal each other. Since this is a calculator problem, I'm going to go and do this on the calculator. So I took a moment to enter both of these functions in my y1 and y2. F is in y1, g is in y2. Now I'm going to see where they intersect. I'm not really sure what window I should use, but I have a feeling they intersect fairly close to the origin. So let me just do zoom 4. I can always zoom out if I need to. So there's my cubic, there's my line. This is the R region in here. So let me now do second trace, option 5 for intersect. Let me move my spider closer to this intersection right here. That's the one I want, because there's a few intersections. So press enter 1, 2, 3 times. And that gives us an x value and a y value. I'm actually going to store both of these. So my x value, it looks like, is 1.940. And I'm going to store that as b on both the paper and my calculator. So whenever I write b, I mean this number right here. Let me actually go back to my calculator and store that. And let's see here. Well, let me just show you what I'm about to store. We also have this y value, 1.455. And I read ahead a little bit on this problem, so I happen to know I'm going to need this y value for later. Reading ahead is always a good idea. So I'm going to store that y value as c, again, on both my paper and on my calculator. So let me go back to my calculator, and I'm going to store both of those now. Let me quit out of my graph. And if you just press the store button, you'll get the x value that you just got from the intersection. I'm going to store that as alpha b. Press enter, so now I can pull that back anytime. And if you want to get the y value that you just got, you have to press alpha y. And let me just press enter to make sure I'm actually getting what I thought I was. So if you press enter, indeed we have that value, 1.4553. So I'm going to go ahead and store that as alpha c. And that way I don't lose these. I can use them whenever I want. Okay, so now to find this area, I need the integral from 0 to b of, and now I need to do top function minus bottom function to get all these distance strips that I'm adding together. So that would just be f of x minus g of x dx. So this is why I named those so I didn't have to rewrite them ever again. This is a calculator problem for sure now. So back on the calculator, I'm going to now do my integral, math 9. We're going from 0 to alpha b. And then in here, I need to do f minus g. So that's going to be, on my calculator, basically y1 minus y2, because that's where I stored those. So alpha trace y1 minus alpha trace y2 dx. So I'm saving myself a whole lot of rewriting on the calculator by storing things. And we press enter to get 4.515. For this part of the problem, I want the volume of the solid generated when r is revolved around the x-axis. Okay, so since I'm revolving around an axis, since I have a solid revolution, that means that I have to add some area slices together that are going to either be washers or discs, pancakes or donuts, and I need to find out which one. So to tell the difference, I notice that r has a gap between that and the axis of revolution. It's not flush against the axis of revolution here. So that means I'm going to have to use washers. So my area formula that I'm going to be integrating, I'm going to write a of x equals pi times big R squared minus little r squared. But now I have to express these in terms of x to actually use it on my calculator. So big R, that's going to be the distance from the axis of revolution to the further away part of the bounded region. That's going to be this cubic function up here, which I've stored as f of x. So I can start writing all this out as pi times, and now I'll put in a bracket f of x squared. And now little r, that I'm going to be squaring and subtracting, that's the distance from the axis of revolution to the closer part of the bounded region. So that's this g of x function that I've written down. So I'm going to subtract g of x squared, and I defined f of x and g of x back in part A. Again, f of x was this top function, g of x was this line right here. So now to integrate, so to do this on the calculator, my volume is going to be the integral from 0 to this intersection x value, which I called b and found back in part A. And then that's going to be just a of x dx that I'm integrating. So now let's do that on the calculator. To make things a little easier on myself, I'm going to do most of my work in my y equals on the calculator. So for this a function, I basically need pi times f of x squared minus g of x squared. So to do that here, notice that I have f of x entered as my y1, g was my y2, so I'm doing pi times y1 squared minus y2 squared, and I did alpha trace to get the y1 and the y2. Quitting out of there now, I'm going to just do the integral. So math 9 from 0 to b, alpha b, of, and now I can just do alpha trace y3. That's where I stored my area function, dx, and that comes out to 57.463. For the last part of this problem, they want me to write an expression but not evaluate something to give me the perimeter of R, and it's going to have some integrals in it. All right, so I know that I've got this distance right here along the y-axis, and I've also got this line here, which I can find with the Pythagorean theorem. And then I also have this curve on the top that I'm going to have to find the arc length for. Since I know I'm going to be doing an arc length formula in there somewhere, I need to figure out the derivative of this function, which is just going to be, so I called this function f, so f prime them is going to be 4 minus 3x squared. So now I can quickly refer to that derivative. So for my arc length then, let me take the easiest side first. That's this side on the y-axis. So this is just the distance from the origin to where we're hitting the y-axis, the y-intercept of this f function right here. If you plug 0 in for all the x's, you end up with a y value of 1. So this is just a distance of 1 right here. Next, the next easiest thing is this line here. So to get this distance, I'm just going to use the Pythagorean theorem. So basically, you have a triangle with whatever x and y value you have at this intersection spot right here being your base and your height of the triangle. Well, the x value of this intersection, we called that b when we found it back in part A. And I also found the y value here in back in part A just because I was looking ahead. And you might recall that I called that c. So this is just going to be the square root of b squared plus c squared. And again, I've already defined b and c back in part A. Now I need the arc length of this thing. So that's going to be the integral from 0 to b of, and now I need the square root of 1 plus f prime of x squared dx. And this is it. They said write an expression, but don't evaluate, and I'm going to take them at their word. No evaluation happening here.